All right, so we can end this section. I'm going to post MIPS code that does this, and MIPS code that does this for the global array, and also another file for MIPS code that actually uses both. So a loop that accesses both the local and the global, and you can look at that and study it. What I want to do in this last video, I want to talk about a few new commands that we haven't talked about. We don't have too much time, but I think that should be enough to cover those few simple commands. So one command is called shift left logical. And shift left logical is relevant because it multiplies, it's one way to multiply numbers. So if you have a sequence of a binary, let's say, for example, you have 1, 2, 3, 4, 5, 6, 7, 8. And let me just do something here. Okay. Let me actually just do 8 bits. Yeah. When you shift left, when you shift to the left, and that would be shift left logical, what you're doing essentially is you're adding a 0 to the right, and you're dropping this, whether it's 0 or 1. So let's say maybe it's a 1 here. If you take this one and shift it to the left by 1 position, that means you drop this and you add a 0. Okay, so let's do a few examples. Let's start with 5. This is 5. It doesn't really matter how many bits you have for now. And if you were to shift this to the left by 1 position, that means you're going to drop this 0 and you're going to take all of that and put a 0 on the right. Does that make sense? Give me a thumbs up if that makes sense. That's called shift left logical. It's an operation that you can do in MIPS. Do you know what this operation does? I mean, what happened to the number? Can someone tell me? And we started with this, which is 5. We ended up with this, which is 10. What happened? So it does double it, which is really multiplying it by 2. And if you add another 0 and remove this, it'll double it again. So it'll multiply it by 2 again. So in this case, you end up with 20. This is 20. We can check. That's 1, 2, 4, 8, 16. So if you take 16, add 4 to it, you end up with 20. So if you have a number like S0 that you want to multiply by 4, you can actually shift left logical by 2 positions. You can say SLL, which is shift left logical, and you can put the result in T0, and you can say I want to shift S0 by 2 positions. Let's do that in the simulator. It's better. So I'm going to say add immediate S0, 0, 2. And then I'm going to say shift left logical. I want to put the result in T0. And I want to shift S0 by, say, 3 positions. So 2 is going to become 4. Then it's going to become 8. Then it's going to become 16. So if I run this code, T0 should be 16. Let's run it. I'm going to run the whole thing at once. So you can see that T0 is 16. Okay, so this is one operation that's good to know, because that's like you can multiply using this. You can't multiply by any number. You can multiply by 2 or 4 or 8 or 16. But that's like what we've seen today, in the cases that we've seen today. That's really what we needed to do. We needed to multiply by 4. So we could have used this one as opposed to adding it, to itself 2 times. All right. So there's another instruction, or rather kind of suite of instructions, and these are called bitwise operations, bitwise logical operations. And these are things like or, and, exclusive or, exclusive and. Actually, there's no exclusive and, just, and, or, exclusive or, and maybe things like nor, maybe something like NAND. You haven't seen those, but we can talk about them today. I think we have time to do that. So the ones that you probably know are and, or, exclusive or. Exclusive or means that one of the two needs to be true for the whole thing to be true, but not both of them. If both of them were true, then it's going to be false. So we know the truth table for and, we know the truth table for or. For the truth table for exclusive or looks like this. Kind of true, exclusive, or false. That's going to be true. Let me do that. That's okay. False, exclusive, or true. That's going to be true. False, exclusive, or false. That's going to be false, just like the or. And false, or rather true, exclusive, or true, that's going to be false. So this is different than the or. Because in the or, true or true will be true. So this is exclusive or. We know and, we know or. There's something called NAND, and NAND is a knotted and. So it's like a negated and, or knotted or negated and. So essentially you would AND it, then you would flip the results. So true, NAND, false, false, NAND. Let's list them first. True, false, NAND, false, and then false, nor NAND, or rather true, NAND, true. Now here we can have a no or nor. Yeah, we can have a nor, which is negated or. And this one's true nor false, false nor true, false nor false, true nor true. So in this case, when you AND them, when you AND true and false, you end up with false. That's what happens, because with AND, both of them have to be true. So when you AND true with false, you end up with false. But when you negate that, you end up with true. So again, you want to AND and negate. So ANDing these two will give you false, but you negate that, it ends up with true. ANDing these two will give you false, you negate that, it ends up with true. ANDing these two will give you true, you negate that, and it ends up with false. Now here, ORing these two will give you true, you negate that, you end up with false. ORing these two is true, you negate that, you end up with false. ORing these two, you end up with false, you negate that, and you end up with true. ORing these two will give you true, not true, or true is going to give you true, you negate that, it gives you false. Does that make sense? Let me see if you have any questions. Give me a thumbs up if all of that makes sense. Okay. So those instructions exist, most of them, not every single one of them. Let's try the AND. So let's say add immediate is 0, 0, 5. Add immediate is 0, rather S1, 0, let's say 10. So the 5 is going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 0, 1, 0, 1. The 10 in 32 bits because that's the size of the register. It's going to end up like this. Okay. So if you try to OR those, this one's going to be a bitwise OR, meaning that each two corresponding bits will be ORed. So this one will be ORed with this one. This one will be ORed with this one. And you know what? Instead of using 10, let me use 11. I think that'll make it slightly more interesting. And let me do the OR. So I can say OR. You can see it says bitwise OR. And I can put the result in T0, and I can say S0, S1. Now what's going to happen here is all of that will be 0 because you're ORing 0 with 0. And when you get to this one, you have a 0 or 1. So that's going to be 1. 1 or 0, 1. 0 or 1, 1. 1 or 1, 1. So you're going to end up with what? 15 here. So if I hit play, you end up with T0 being 15. All right, how about the AND? What's going to happen if I AND? Give me the answer in the chat. And let me put it in T1, S0, S1. What's going to happen here if you AND? You have to tell me before I get to the answer. Well, you're not fast enough. What's going to happen if you AND this with that? What are you going to have? So do a bitwise AND. When you AND this 0 with this 0, what do you have? 0. When you AND 0 with 1, what do you have? 0. When you AND 0 with 1, it's like you're ANDing false with true. It's like you're saying false and true. False and true is going to give you false. True and false is going to give you false. False and true is going to give you false. True and true is going to give you true. So that's the one. And I was hoping that you would give me the answer. You did give me the answer eventually, but let me pause here. I'm sensing that there's something that you're not understanding because this was an easy question. Give me a thumbs up if all of it makes sense right now. Okay. Okay, you can do exclusive OR if you want. I guess let's do exclusive OR. This one is your chance to prove to me that you understand this one. So I'll give you a few seconds to tell me what the answer should be here. Okay, so Anthony's saying 14. That's good. This is correct because if you do exclusive OR, and again, we're doing it for these two, this will give you true, this will give you true, this will give you true, and the last one will give you false. So you end up with 1110, which is 14. And we can play and hit, and you can see that T2, which is really the register here, the register that I use this T2 is going to be 14. So you can check those instructions out. You can try exclusive or immediate. You can try AND immediate or immediate. You can even try the NAND or the NOR. So that's interesting. That's hard to remember, but we don't have a NAND, we have a NOR. So we don't have a negated AND. I mean, the negated AND exists in the hardware. It's very important, but we don't have it as an instruction. We only have the negated OR, the NOR. Now, this NOT is actually not a pure instruction. This is a pseudo instruction. So if you want to negate something, and if you don't want to use a pseudo instruction, you can use one of those that we learned. You can actually use the NOR, which we did learn kind of here, but we haven't used. Or you can use the exclusive OR. Yeah, you can use the exclusive OR. And the idea here is we can do it with the NOR. Doing it with the NOR is actually going to be slightly easier. What you see here, you see a pattern here, an interesting one. That's actually the case for both the negated and the negated OR. And that is, if you take something and if you NOR it with itself, you're actually getting the opposite. So if you take true and NOR it with true, you end up with false. And if you take false and NOR it with false, you end up with true. So for example, if you want to take this sequence, and if you want to flip everything, you can NOR it with itself. So I can NOR, I can put it in T3, and I can NOR T2 with T2. This, by the way, is not a hard number to kind of calculate, and maybe I'll give you a minute to do that. But if you NOR this with itself, it'll be like, again, you're NORing it with itself, and 0 NOR 0 is going to give you 1. And then 1 NOR 1 is going to give you 0, and 0 NOR 0 is going to give you 1. So this is what you're going to end up with. Can someone tell me what this number is? Think about it for a minute. What is this number in decimal? Of course, assuming that this is 2's complement, which is really what it is. So this is 2's complement, it's negative. So for all of those numbers, they were also in 2's complement, but they were positive. So we just looked at the bits and we converted them to decimal. For this one specifically, it's going to be negative. So we need to do something. I'll give you a few seconds to think about this, and then we can hit play and verify your answer. Okay, Anthony, you're right. So Anthony, you said negative 15, you're right, because when we have a negative number, we swap, add 1, then convert. If you swap all of that, you end up with really what you started with, which is that. And if you add 1 to it, you end up with this. And when you take this and convert that to unsigned, it'll be 15. You add the negative sign, it'll be negative 15. So if we hit play, assemble and play, ideally T3, hopefully T3 is going to be negative 15. Let's see. Okay, let's look at T3. You can see it's negative 15. Perfect. That's correct. All right. Do you have any last minute questions before we stop the recording? Okay. All right, we can stop it here. Again, thanks for attending those videos, those recordings, those Zoom sessions, and I will have a good weekend. I will talk to you on Monday We do have an exam on Mondays, so don't forget that. Feel free to email me anytime if you have any questions.